Good evening and welcome. Here we are in hour 31, I believe. We're into our last week of this course here, or so, last week and a half. Today I want to finish off chapter 10 on vibrational motion. We're going to talk about solving simple harmonic motion problems. We've got some examples of that, some questions from the class. Damped vibrational motion, that's what this photograph is about. So in your car, there are shock absorbers, which are springs, which are attached to the wheels of your car. The purpose of those springs is so that every time you hit a bump, your whole car doesn't get thrown around. The springs absorb the shock of hitting bumps. But what you don't want to do is for every time you hit a bump for the car to start into a vibrational motion. So what they do is they'll purposely damp it. So damping just means that there's some friction. In addition to a force, from Hooke's law, there's a second force, which is a frictional force, which opposes velocity. And so what they do is there's a piston with some very viscous oil in it, which produces a frictional force which slows the vibrations. And so one way to test if your shock absorbers are actually calibrated the right way is that they shouldn't oscillate up and down. So on the subject of oscillations, a grandfather clock, the way it's driven is that there is a pendulum. A pendulum has a very specific period. And once again, it's given by, I think it was period is equal to 2 pi times the square root of L over G, I think it was. So that's true for any mass that is a distance L hanging from its rotation axis and it's oscillating through small oscillations. That's driving this clock. If the clock was calibrated, so the length of the pendulum adjusted down at sea level, wherever it was originally, I guess, delivered to Canada and Halifax or something, but then it was shipped to Calgary, would the clock run fast or slow or normally as it does? I will give you a minute to think about that and then pair up and share your answer. Okay, see what people are saying here. And stop. Okay, so I think it's B, but let's check it. So I think that the idea is that T is equal to 2 pi times the square root of L over G. So the big question is, what is the difference between being by the sea or being in Calgary? Does anybody know? Somebody's yelling out G. What's the difference between G in Calgary and Halifax?
What?
G's 9.8, isn't it? What was the comment? I missed the joke, but okay. Well, let me just tell you what I think. So what I think is that you have a yes. Back up at the back row.
Oh, is it because it's above sea level, so G smaller than?
Yeah, I think that's right. I think it's like 9.81 at sea level, but as you go further from the center of the Earth to a higher altitude, it becomes 9.80. I think in Denver it's 9.79 or something. There's a slight reduction in this value of 9.8. So good. So G is slightly less, and that's all it takes to throw your clock off, right? Because it's ticking every single second. Slightly less. So if G is down, and it's on the denominator of this, that means T is increased. So instead of going tick, 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 it goes tick, tick, tick. Does that make sense? The time between ticks is less, so that means like after a minute, it's only ticked 59 times and then it takes another, so I think it's running slow. And it will lose time, so that by the time it says it's 5 o'clock, it's really 5:15 or something, and you're late for class. Make sense? Slow clock. Okay. So I'm going to show some comments that got typed into Learning Catalytics on the please enter at least one specific question or concern you would like me to address in class question. What is the weight of each chapter on the final exam? Good question. so this is maybe more than you want to know. It's a comprehensive final exam. You have to know everything. We started from September. In chapter 2, we went right through. We're going through chapter 11. So that's the short answer. The long answer is that there is more of a weighting on chapters 8, 9, and 10, and 11 since you haven't been tested on those yet. Does that make sense? I don't know if this is helpful for you, but if you do want to focus a little more on the later chapters. Does the exam follow the same format as the midterms? The answer is definitely yes. It's exactly the same format. It's just a little longer. Well, it's twice as long. We're going to use 24 of those multiple choice scratchy card things, but you have 3 hours, and the 4-step model. 2 of those questions with the 4-step model. Will we have an aid sheet for the final exam? This is a good question because the answer is yes, but... So you want to know the but? There's a but. But you only get one. So you have to consolidate. This is a little less area, I think, like per chapter or something than you had for the midterms, right? Like half as much or less. So I think just put on the stuff on your aid sheet that you think that first of all you don't want to memorize. I might just memorize F equals MA, but those things that come up a lot, like the kinematics equations, you don't feel like memorizing them, but they're very useful in solving problems. Put it on your aid sheet and keep it well organized. Please make the final easy as we are all suffering. So my answer is not ha ha ha, but it's it's literally, I already had to submit this. There was a deadline, and we had a meeting, and I'm not in class, but I want to participate. These are things that I read every day. So, yeah. Maybe you should come to class then. I don't know. You're paying to be here. Anyway, I'm stressed, so I get that a lot. All I will say is that, I do understand that it can be stressful to be a student, and I was there, and, I do wish that students could spend less of their time thinking about their marks and more of their time thinking about physics. But I do understand that marks are important and your GPA is important to you, and that they can cause a lot of stress. But I recommend you have a circle of friends, you try to talk to people. If you just try to bottle things up, the problems don't get better, they usually get worse. Oh, this is a question about, do you have to put all those rotational inertia things on your aid sheet? Does anyone know? It says no, because I've actually photocopied table 9.5 from page 263 of your text. That's the one with all the, I can even show it, I guess, if I press the dot cam thing. Right? Dot cam. Send. Page 263 has this table. So you will see this on the final exam. It's that one. Okay? I'll just photocopy that and put it right on the front page of the final exam, or page 2 or something like that. Since we skipped 9.6, is it going to be on the final exam? Another excellent question. Let's give you a complete list of what we skipped. First of all, we skipped 2D projectile motion. Secondly, we skipped Kepler's laws. Secondly, we skipped tides and the Earth's day. Now, we didn't skip this yet, but I had to already make the final exam, so I was looking ahead and trying to estimate, and I couldn't figure out whether I was going to get the Doppler effect or not, so I just didn't put it on the final exam. So I don't know if we're going to skip. I guess we might as well skip it since it's not on the final. So at this point. Anyway, so it's not on the finals. I'm telling you. Yeah, so no, so I don't know where December 4th came from. So my last class is on December 5th. We'll be sitting here 1 week from today, and we'll be saying goodbye. Let me cry a little. I didn't hear that. I have feelings too, When do we get our test back if we ask for a remark? So if we made a mistake in marking your test, we will fix it. We guarantee it. We will fix it. So we have a stack of them. Is this the last practical? That's a good observation. Yes, if you're doing practicals this week, this is the last one. and you're doing evaluations of your practical TAs. Is the Earth flat? So, okay. This is just like a philosophy. You guys are U of T students, okay? You know, the Earth is a sphere, vaccines save lives, climate change is caused by human behavior. You know, these are things that, you know, they're not a conspiracy theory, they're based on our observations. Like time zones, for example, call China. You know, there's got to be something going on there if the sun is down and up. Anyway. Okay, so that's, I don't know. So this is, the next one is, I'm going to do a little problem for you. Homework 9, question 4. This is the one that, trying to focus it a little better, that had a mistake, I believe, on the mastering physics. And a lot of people have been asking me to explain this. So let me explain it. You have 2 disks cut from the same uniform board. And the radius of B is twice the radius of A. And they can rotate around a fixed vertical axis. There are 2 very light battery-powered fans on the edges of the disk, and they're both switched on, and FA, I guess, equals FB. I'm going to just call that F. It's the same force on both. But the radius of B is 2 times the radius of A. And also, they are cut from the same uniform board. It says that in the question, and I think what that means is that they must have the same density. Or, I guess, mass per area, perhaps. So I'm going to express that as an equation that the mass of A divided by, like I guess the pi RA squared, the area of A, should equal the mass of B divided by the pi RB squared. So they're both circles, so their areas are pi r squared. And I think this is where mastering physics made its mistake. I think it was assuming that these both have the same mass. And I can imagine that perhaps if it was made of moldable clay, and you had a disk of this particular radius, and then maybe you squished it so that it was flatter, but then, you know, got squashed out to a larger radius, kind of like a pizza pie, you can stretch it out. It might have the same mass, but have a larger radius, and then their answer is correct, I think. But that's not what they said. They specifically said it's cut from the same uniform board. So I'm sure their answer is wrong. So anyway, I think the pi's cancel here, which is nice. But you do get this ratio, and if you want to, we're solving for the B in terms of A things, so let's do that. I think we get that mass B is equal to RB squared divided by RA squared times MA. And since we actually know that, that implies that MB is equal to 4 times MA. So that's sort of what I'm getting from that statement. And then I will use Newton's second law for rotation. That's what this problem is really about, for rotation, which is that alpha is equal to the sum of the torques divided by the rotational inertia. And these are solid disks. So if we look at that table, which is going to be on page 2 of your final exam, you'll see that for a solid disk, I is equal to 1/2 mr squared. Okay. So now we just do it. So, alpha A is equal to the torque, which is F times RA times, I think, sine 90 degrees. I'm going to assume that the angle between the radius and the force is 90 degrees in both of these cases. They're both directed sideways to the edge of the disk, like a tangential force. And sine of 90 is 1, so it all works out. And then divided by the rotational inertia, which is 1/2 MA times RA squared. So sine 90 equals 1. You end up with this RA cancels this. There's some cancelizations. Let's cancel, cancel, cancel. And I'll bring the 2 up to the top, so it ends up being 2 times F divided by MA/RA. And then the rotational acceleration of B is equal to, and I'll push this up a little bit, again, F times RB times sine 90 divided by a half MB times RB squared. So that equals 2, same sort of cancellations. The 90 goes to 1, and the RB cancels the RB squared. You get 2 times F divided by MB RB. And so rearranging, theta B is equal to 2F divided by 4MA, because that's from there, and then times 2RA, which is from up there. And you end up with an eighth of 2F divided by MARA, which is, alpha A divided by 8. And so this is that alpha A is equal to 8 alpha B. So that's how I got that. Did you have a question at the back, or just stretching? So several people asked me to go through that question, so I think that's how that works. Any questions about it? We ready to go back to my laptop for more jokes and hilarity? Just a little more. And I will scan this right after class, promise. Yeah, this is one that I thought was funny. So, somebody, I guess, doesn't have Angela's contact information, so used learning catalytics to send a message to Angela saying that he's going to skip class. And so Angela, just let you know, maybe give Gary your phone number next time. Okay. So the next question was 65% in each section. I scratched my head trying to think what this is about. Does anyone know? Exactly, about the course evaluations. Yeah, so good call. So it's, remember, the 65% of you have to evaluate me in order for all of you, 100% of you, to get the plus 1% on the test. So it's not looking so great so far, but there's still lots of time. It goes till Friday, December 7th. Maybe you could raise your hand if you've already done this. Did you do your course evaluations already? No, if you're not raising your hand and people are glaring at you, then then you know why. It seems like more than 35% of you, but you're here. Let's just process that for a minute. Are we on to something else here? Okay. All right. So back to this pendulum business. It's been mentioned that this period is 2 pi times square root of L over G. Also the frequency is 1 over the period, so it's 1 over 2 pi times the square root of G over L, I think. Anytime you have something that's swinging, and in fact when a biped walks, or even when quadruped walks, the legs are kind of swinging back and forth as you're going along. If you think of your reference frame in which you're at rest, then that's what's happening. And so there's some sort of a natural walking frequency. And you can calculate that, and once again, that L is sort of an effective distance between the rotation axis, which in this case is your hip, and the center of mass of your pendulum, which in this case would be your leg, right? So maybe the center of mass of your leg is half a meter down. If that's the case, the frequency is about 0.7 hertz according to this equation for a human. For a giraffe, it would be longer because this distance between hip and center of mass of the leg is a lot longer. So their strides have a lower frequency as they're walking along. And you can definitely see it if you see one of these little dogs, you know, their legs going as they go along at a very high frequency for the same reason. And I have another example. Well, yeah, this was one, some people saw it in the pre-class notes from last time. which was, shove that over there, see if I have room. Luke and Leah have a combined mass of 120 kilograms, both grasp a rope of length 30 meters that is attached to a beam above them. The beam is halfway across a 10-meter horizontal gap, and they want to swing across. If they start from rest and swing down and up, just reaching the other side, how long does this take? So I don't know if you can picture this, but this is a kind of a Tarzan kind of swing thing. Here's the beam, and here's like where they are. And there's a rope, which is 30 meters. And then they go, oh, and they go over to this side to the bridge. And the question is, how long, so how much time? And this is actually from a movie in which they're getting shot at by stormtroopers or something like that, and there's a deathly chasm and all that. So, but they swing across, and it all works out. So I've had students going, they come to office hours, and they've set up the force body diagram, and they're trying to figure out the acceleration and use quit anyway. So watch how I do it, because it's going to be really, really ridiculously simple. What I'm going to do is say, let's assume, so this is 10 meters, by the way, and their mass, that's another thing. Mass is 120 kilograms, 10 meters. Assume simple harmonic motion, and then this problem becomes really simple. Okay, this is a simple pendulum. L is equal to 30 meters. Okay, small angle approximation, small angle oscillations or vibrations. And what's happening is that the period is the time for one complete oscillation. So that would be if they grabbed onto the rope and swung across and then swang back to where they were getting shot at in the first place. So that's too long. You want to just do half that. This is both ways. Okay, and t equals t over 2 is 1 trip. So that's it. So the period is, from your aid sheet, 2 pi times square root of L over G. Is 2 pi times the square root of 30 over 9.8. So t is 10.99 seconds. So t over 2 is 5.5 seconds. And that's how I did it. So much simpler than you thought, right? You're just using this basic equation from your aid sheet. And one of the ways I might evaluate that is I might say check. Is theta max less than about 10 degrees? Remember I told you that it had to be less than about 10 degrees in order for us to make the small angle approximation that sine theta, which was the right answer, was approximately equal to theta, which gives you simple harmonic motion. So I guess you can try to draw that triangle out. If I push this up a little bit more, maybe it's like this is your 30 meters, and if it's 10 meters all the way across, then maybe this is 5 meters. And here's your theta max. So like sine of theta max is 5 over 30. So theta max is sine to the minus 1 of 5 over 30. So I got 9.6 degrees. So this is okay. It's less than 10, so I guess it's probably okay. It's about 5.5 seconds. Keeps everything, all your mistakes to within about 1% if you keep the angle to less than 10 degrees. Are there any questions about that? Yes?
At the bottom 5 meters. Isn't it 10 meters across?
Yeah, but that's halfway, I guess, to get because the angle is always measured from straight down, which is equilibrium of a pendulum. Make sense? So the angle, the maximum angle, is measured from straight down. It's an excellent question. So that's why I used 5 meters and not 10. So it actually swings between minus 9.6 and plus 9.6. Any other questions? I'm going to go back to my laptop. See where we're at here. Oh yeah, we're going to do a, so let's send this to the front. And here's a learning catalytics question for you. Let's say, kind of like in my Excel spreadsheet, that we have a 1 kilogram mass attached to a horizontal spring with a spring constant of K equals 1.0 newtons per meter. And when the mass is at x equals 0, that's when the spring is in equilibrium. We'll pull it off to 1 meter and release it from rest. So that's at plus 1 meter. How many seconds will it take to get all the way back through equilibrium to the minus 1 meter to the other side? This takes a little bit of calculation, but it's not too bad, so I'll give you a minute. And then I'll show you why I've done this as well, because it's kind of, I was playing around with Excel. Anyway. Okay, so what I got here is that in this case, it's not L over G, its period is equal to 2 pi times the square root of m over k. Remember that? But this was just 1, I think, right? So it's just t equals 2 pi. And so if x is equal to a times cosine of 2 pi over capital T times little t, and a equals 1, m equals 1, k equals 1, etc., all these things equals 1, then I think if you look at it, it's going to start here. This will be 1, this will be minus 1. It'll get down here at t over 2. So. Okay, and here's t. So it'll be t is equal to 2 pi divided by 2 is pi. So, and the reason I thought I'd just show you this is because I was worried a little bit about my time step. Remember the time step was 1/100 of a second? I thought maybe that's like too much. So what I did is I typed 0.00001. So this is like 1/100 of a millisecond time step now for that same mass. And then I pressed Control C and Control V for like 100,000 things. So you see it's really smooth. But anyway, this is what I do sometimes late at night. And then Excel was like swirling around for like a long time. There was this little circle, and I was, what's going on? Well, it was computing. And I guess that's where the noun computer has the word compute in it. So it must have been doing all this work. It eventually got down, and this is the funny thing, is I thought, well, where does it get down to minus 1? Well, it goes beyond minus 1, and I don't know why. I think it's because my numerical integration is inherently crappy. I'm always using the velocity from the last time step, and somehow it's violating conservation of energy. But if you look at where does it get to its lowest point? Well, it's negative 1.0000132682386. It's getting more negative, so it's still going down. So where does it stop getting negative? Or where does it stop becoming more and more negative? You keep going. Oh, wait, it's going back up? Yeah, it's getting less negative. I missed it. Somewhere in there. Because when I found it, I was rather surprised. Still getting more negative. More negative, more negative. And then that's as negative as it gets, right there. And so it's at t equals 3.14159 seconds is when it gets to its lowest point. So I have just written an Excel spreadsheet that calculates pi precisely to 5 decimal places. And I did it by accident because I was just trying to do a mass on a spring. I don't know, I laughed a long time about that. It's pi. Okay. There's something profound there, I think, but I don't know what it is. Okay, next thing is this statement. So now we're getting into the last two sections, or the last section, I guess, of chapter 10, which talks about damped and driven harmonic motion. So anytime, and there's a question from one of you today, which is, what happens, is it still simple harmonic motion if the amplitude changes with time? And the answer is no. When we say simple in the simple harmonic motion, we mean that it's cosine forever. It's this equation, and A is a constant. But in real life, A is not a constant. And so that's called damping, and this is sometimes called damped harmonic motion, DHM or something, instead of simple harmonic motion. So that's what we're talking about now. It's often characterized by a cosine multiplied times something which then decreases. And sometimes it's an exponential decrease. But we call this, there's sometimes an envelope function. Anyway, damping is a useful aspect of the design of vehicles and bridges. We want to often damp out vibrations. And Atkina goes through three types of damped harmonic motion. There's underdamped, overdamped, which is kind of like not enough damping, too much damping, and then in the middle is called critical damping. It's the just right. So if it's underdamped, what that means is that it's still oscillating. That's all. It crosses the zero position and then comes back towards equilibrium. And it does that sometimes a few times. And this dashed line, again, is sometimes called the envelope. Just write that on there. Sometimes I see this word tossed around, envelope function. The envelope is often some sort of exponential decay. It's showing that friction is taking away that energy, and the amplitude is decreasing. But there's also these next two, which look exactly the same to me, but the idea is that if it's overdamped, then it goes to zero without crossing zero, but it takes a long time. And if it's critically damped, it does the same thing, but it goes to zero as fast as it possibly can. And if you decrease the damping anymore, it would overshoot and oscillate a little bit. So this is just the place between where it crosses zero and where it takes a long time to get to zero. And that's it. I guess I could give you a learning catalytics question, which is a little bit of review of chapter 10. Let's do it. That should be on your device. A 5.5 kilogram cart. So this is, I'm going to give you like 2 minutes for this one because you have to calculate something. It's attached to a horizontal spring, the other end of which is attached to a fixed bumper, so a wall. So it's simple harmonic motion. The spring constant is 150 newtons per meter. The cart is pulled to the side and released from rest when the spring has been stretched by 0.035 meters. How much mechanical energy is converted into this internal thermal energy before the cart stops oscillating? So I'd like you to think about that. Think about there's one specific equation that's going to work here, I think, best for you, a way to do this. And feel free to discuss with your neighbor, and I'll give you 2 minutes to work it out. You may need to grab a calculator. Most important. And I think the concept here is, so going once, going twice. Is that the total energy, yeah, it was A. Initially, E total, I guess, is just all equal to the spring energy, which is 1/2 K times, I guess, X initial squared. And then finally, it ends up at equilibrium. So E total equals 0. It's at equilibrium and stop. It starts off with 0 speed, and and a bunch of energy in the spring ends up with 0 speed and no energy in the spring. So that's what happened here, is that somehow friction dissipated the energy that you initially stored in the spring. So that's all that was about. So you get it 0.5 times 150 times 0.035 squared. And that's where I got the 0.09 from. Any questions about that? Yes?
The option is not there on the actual question. That's why you select it on there.
I see it as A.
No, it's not there. Like,
Oh, yeah, the pre-class? Okay, yeah, that might have been, sorry about that. Sometimes my pre-class options are bad. Okay, so yes, go ahead with the questions.
So for the question that we just did, wouldn't you multiply another 0.5? Because the constant is, wait. Oh yeah, the mass is, no, never mind.
Got it? It's okay? Okay. Last section, driven oscillations and resonance. So the idea here, I'll just leave that up here. I want to do the demo. So here, let's do a demo. So this is, these are a bunch of saw blades and they have different lengths. So the idea with the saw blade is you take it over like this and you release it and it goes boing, oing, oing, oing. So that's the physics there. And a shorter saw blade has a shorter frequency. No, shorter period, higher frequency. You get it right. The longer the length of it, and I guess the bigger the mass or something like that, the longer the period. So that's a low frequency oscillation. If you have a shorter saw blade, same kind of saw blade, it has a shorter frequency. God, I haven't had dinner yet, sorry. It has a shorter period, right? So a higher frequency. Let's see if I can do it right. Third time's the charm. That's a long period, so low frequency. This is a short period, so high frequency. Now, so that's the natural oscillation frequency of these things, and they get sort of less and less as you go along. So now what I want you to think about is the concept of resonance. And you all learned this on the playground when you were on the swing. And you have someone pushing, or if you ever push a child on a swing. The swing has some natural frequency. And then if you're pushing your child, you can be an external force, which is a driving frequency. And you can do that at any frequency you want. You can do high frequency pushes, in which case the kid is just getting pushed around, nothing much happens. You can do low frequency push, which is push, read my phone, oh yeah, push, read my phone. Okay. None of those work. But if you push at exactly the right frequency that the child already wants to swing at, then they start going higher and higher, and eventually they're clunking you in the head and knocking you on the sand, and they're laughing their asses off. So that's the phenomenon of resonance. You have a driving frequency because you're doing a periodic external force for some reason, and you have a natural frequency. And if those two match, then the amplitude of the oscillations can go way up. So I'm going to turn this, and what that does is this goes round and around, and it's connected to this, which shakes this just a little bit. It's a small, it doesn't have to be much. The external driving force, and you can do this always frustrates my children when I push them, is I give them a tiny little push, and they're like, push harder, Dad. And I'm like, just wait. Because if you just keep pushing at the right frequency, eventually they're really going up, and their mom's yelling at me, hey, they're going too high. So, okay, let's do it. So if I can get it right at the natural frequency of the big sawtooth, and that's the natural frequency of the big one. So let's increase the frequency. There's the second sawtooth. There's the third one. As I increase the frequency, I'm going up the sawtooth blades. That's third. I'm matching a resonance. Let's go to the fourth one. Fourth one. You see it? Let's go to the fifth one. There's the fifth one. I've tuned it. And then see if we can get to the last one. Last one. Well, I don't know what happened there. Anyway, you got it. So that's how a lot of things work is by resonance. And the basic idea is that the amplitude of oscillations for all the other saw blades that are not matching the driving frequency is not very high. So external frequency is different from the natural frequency. And the natural frequency, by the way, is exactly what we've been dealing with so far. So for example, f sub 0 is equal to 1 over 2 pi times the square root of k over m, for example. That's a natural frequency if you have a mass on a spring. You could also have a natural frequency of a pendulum, which is 1 over 2 pi times the square root of G over L or something. These are IE, natural frequencies. The driving frequency is whatever you want, and if you match them, then the amplitude rises dramatically, and people do these resonance plots where you plot what your driving frequency is versus what the amplitude of the oscillations are. They go way up when you hit resonance. And there's the, let's do a learning catalytics. Yeah, we have time. So what can happen is that if shock absorbers have a frequency, natural frequency of 0.9 hertz that they want to oscillate at, if you have some bumping that's right at that same frequency, well then your car starts bumping more and more and more because you've hit the resonance of your car. So at what speed does that happen if the bumps in the road are every 10 meters, I guess? This is a bit of a review question. You get me? Let's do 1 minute 20. I'll finish this one up and I'll finish my discussion. 5 seconds. 4, 3, 2, 1, and stop. Someone you'll see. So yeah, so what I was thinking there is that, so you've got your car, and you've got bump, 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 and it's going along 10 meters. The period is 1 over the frequency, right? And I think the speed is going to be this distance d, since the d is 10 meters, divided by the time that it takes to hit each bump, something like that. So it's equal to d times 1 over t. So it's actually equal to d times f, if you think of it that way. So 10 meters times 0.9 hertz. So some examples of resonance. Every musical instrument ever designed works on usually on a concept of resonance. So for example, if you take a bow and you drag it across a string on a violin, that is using sort of stick-slip oscillations on the bow. Someone on their phone or something over there? Get off your phone, please. Just press off. And that is going to produce a frequency which will match the natural resonance frequency of the string. And so it'll make a loud sound. If you have a flute and you're blowing over the I guess opening of the flute, you're setting up little oscillations there, and if those oscillations match the frequency, the driving frequency matches the natural resonance frequency of sound waves in and out of the tube, depending on where you put the holes, then again it makes a loud sound. Also, if you take a wine glass and you flick it, it makes a little ping sound at a particular frequency. If you then sing a note at that exact frequency really, really loud, and you match the driving frequency of the sound waves from your voice to the natural frequency for the glass, it can break the glass, apparently. Though I've never done it. In 1947, they built a suspension bridge over the Tacoma Narrows, which is in Washington State. And this is a true story. It had a resonance frequency. And it turned out that gusts of wind coming down that channel had a driving frequency. And unfortunately, they matched. And one day, the entire bridge collapsed. And there was one car left on there, and the guy got off, and he sort of managed to crawl to safety, and just barely left with his life. And he left the dog in the car, and so the dog died. So this is not very fun. That's it. On that very somber note, I'm afraid, we're going on to mechanical waves next week. So have a good weekend.